25 is my happy little fish example. Here we have, this is actually a complicated molecule. We have kinetic conditions though. And with kinetic conditions we have a 1,2 product. Now there are actually two possible stable carbocations that are about equivalent, almost exactly equal. But I have three answer choices here that are entirely impossible. So let me show you these stable carbocations here from my little tadpole fish looking thing. Oh my goodness, that's the ugliest. Cyclohexane. I'll go with it. Okay, so the first double bond reacts here to produce this carbocation. And with the resonance structure here, you see this will end up on a tertiary carbon over here on its little tail. That goes back and forth. But here's secondary and here's tertiary. So that has to be the one that actually formed. You see with this other one, if I reacted this, it reacts with the inside ones and the carbocation forms right there, and we'll end up on a tertiary and secondary position here. These two positions, which is identical to this set. So it actually doesn't matter which side reacts here, but you do have to identify that this product here ends up reacting in the 2 spot because we have, what is it, minus 80 degrees kinetic right here, cold temperatures. And in cold temperatures it takes less energy for that Cl to come down and attack the 2 spot. The 1 spot was the one again that where the hydrogen initially added. So there's 1, 2, 3, and 4 positions there. And you can see then once that reacts we form this. This is showing where it reacted with this double bond here, but it reacted against the resonance. That's not going to occur because it's less stable. C is also reacting against the resonance where it reacts up here, and there will not be a resonance structure. D is the crazy answer where the Cl is somehow on the pi bond itself. A little bit crazy. Let me show you B here, just to illustrate. Here B is showing this, that reacts and somehow this carbocation forms against the resonance. This is only a tertiary versus the hybrid of a tertiary and secondary over here. So that is less stable. Does not form. Okay, so A is the answer on that. 26 is another anti-aromatic. This one had a whole bunch of anti-aromatic answers in it. And here the nitrogens have lone pairs on them, but we don't count those towards Huckel's rule because the pi bond, which is the p orbital, is already on the nitrogen itself. So we can't count those lone pairs. Those exist in sp2 hybrid orbitals. And going back to chapter 1, sp2 orbitals only form either lone pairs or single bonds. They do not make up the pi bond systems, only the double bonds. And these are formed from unhybridized orbitals. So anyway, this is completely conjugated now because everything is sp2 hybridized, and it is a ring that fits the first three criteria. And then we have 4 pi electrons. That's the most common number when we're going anti-aromatic here, and that is the answer. 27 is a tricky one, a very tricky one here. What I was mainly expecting with this one was for you to observe first the number of signals, like I went over before. We got 1, 2, 3, 4, 5 signals. And then let me jump to it. Notice the chemical shift here is at 7 ppm or higher for that. That means we have an aromatic compound. That was one of the slides in the notes. Let's look at how many aromatic compounds we have. We can also count the number of signals, but let's do a quick sampling here. We have to determine this is not aromatic. Neither one of these rings is aromatic because we got sp3 atoms in there. This one you can see is aromatic. That's the answer. This one's all sp2 here. It is a ring. The problem is this is an anti-aromatic. How did that end up in there? That conforms to that rule there. And again here, there's a hidden sp3 atom here that makes that not aromatic. So A, C, and D are not aromatic compounds, so they cannot give a signal above 7 for the most part. There are exceptions, of course, but for the most part, they're not all going to appear higher. And let's do a little test here. Let's look at this signal for this one. These 2 hydrogens right here are equivalent. They are not beside any hydrogens here. Let's see. Nope, there's one. 1, 2, 3. There's 1 hydrogen here. They are beside 1 hydrogen. I misspoke. So that should be a doublet. But let's look at the chemical shift here. Chemical shift with a carbon that's attached to an oxygen here is going to be around 4 ppm. We're not anywhere near the 4 ppm range. It actually is cut out because there's no signals there. Okay. The other thing here on C, say you didn't catch that this is anti-aromatic. Let's look at this thing. That one there is a hydrogen that should be around 9. Maybe you thought it was that one. But let's see. Let's look next to it. There's no hydrogens right here. Let me count. 1, 2, 3, 4. No, all the bonds are occupied with carbons right there. So only 4 possible bonds to carbon, again going way back to chapter 1. So this is going to be a singlet. This one here, right here, is not split by the boron there. That one's going to be a singlet. And then these 2 over here, they can split each other now. This one's going to be a doublet. This one will be a doublet. On both of them, the n+1 is 1 + 1 because of the hydrogen next to it, this one right here. So that one's a doublet, that one's a doublet. Let's look at the spectrum. We got 2 triplets and only 1 doublet. Oh, excuse me, 2 doublets right here. This one here is a complex splitting right here for that one. But that one there is a most likely going to be a triplet. So we have 2 doublets, 1, 2, 3 triplets. Let's look at the splitting on this one here. Let me erase this thing. On the right answer, okay, the double bonds can throw you off, but there is symmetry right down the middle of this right here. If you ignore the double bonds, it helps because these are alternating in here. Those are all alternating, so they're not permanent. So this is going to be the same signal as this one down here, and then we have a hydrogen right there too. This one will still be split by that one and the one down here. So that one will appear as a triplet. This one's only by the one hydrogen right here, so that one would be a doublet. Let's draw these in here. This half of the ring is identical to that half. This one still will be a triplet though, because it's by the two hydrogens on the top and the bottom there. This one would be also a triplet, and this one would be a doublet. There's no hydrogens on the carbon next to it because that has 4 bonds. So we have 1, 2, 3 triplets and 1, 2 doublets. 1, 2, 3 triplets. It's hard to tell that that's a triplet. But again, I wasn't looking for splitting on this one here, mostly the chemical shift value, which you could see is above 7.